What's up, folks? This is Rev Bari, Brown University physics graduate student. Welcome to the next episode of Advanced Quantum Mechanics. Today, we're looking at the formalism for special relativity. Now, just as a recap, in the previous lecture, we looked at the Klein-Gordon equation, the first attempt to create a relativistic Schrodinger equation. Unfortunately, it failed because it resulted in negative probability densities. Now, in today's episode, we're going to explore the notation for special relativity, everything from contravariant and covariant derivatives, as well as the Lorentz transformations, so that we can get a good grip, a good handle on special relativity before we try to integrate it directly into quantum mechanics. So, with that being said, let's start off with something simple, a space-time event. So here is an event in space-time. It could be a fly, it could be a lightning bolt, it could be some kind of a bomb exploding, it could be some kind of an event happening at that location. Whatever it is, this is a space-time event. Now, to describe this space-time event, well, I need some kind of a coordinate system. So here is a coordinate system with x on this axis and t on this axis. Now, to describe this event in space and time, I need 4 coordinates. I need 3 spatial coordinates, and I need 1 temporal coordinate. So these are my 4 space-time coordinates. Now, what if I have a second reference frame which is moving with respect to my original reference frame with some constant velocity v? So there's an inertial reference frame right there. Well, then to describe my space-time event, let's call this space-time event E. To describe this space-time event E, I can no longer use the original space-time coordinates, can I? I need new coordinates for this new reference frame, and that's where the Lorentz transformations come in. So the Lorentz transformations include time dilation, so that t prime is gamma t minus vx over c squared. Time dilation comes here, and the relativity of simultaneity comes in over here, where you can see that the time depends on your position, the position of the second observer. We also have length contraction coming in via this second equation, and the other 2 coordinates remain fixed. They are not changed for the y and z directions. Now, we can also describe these Lorentz transformations in matrix form as follows. So I can write my new coordinates, t prime, x prime, y prime, z prime, as some matrix times my original space-time coordinates. So what is that matrix? Well, that matrix is the Lorentz transformation matrix. First of all, I do nothing to the y and z coordinates, so I know they will be both 1, okay? So the real action is going to happen up here. So let's see, let me just fill in the blanks, and then we'll get to the real magic right here, which is in these 2 boxes. So what is going to happen right there? Right there, we're going to have gamma, and in these 2 elements, we're going to have minus beta gamma, minus beta gamma. So let's see if that works out. Does this indeed reproduce the Lorentz transformations? Let's see. So I'm going to multiply this row by this column and see what I get. First of all, this is a 4 by 4 square matrix, and this is a 4 by 1 matrix. So my result will be some 4 by 1 column vector here. So I'm going to have gamma times t. So let's expand this out. Gamma times t minus beta gamma x. Okay, that's my first element. Then for my second element, I've got this second row times this column vector. So that's minus beta gamma t minus, or rather plus, gamma x. And then my y and z coordinates remain unchanged. Let's see if this reproduces my Lorentz transformations up here. First of all, I can neglect this c squared since we're using natural units, and we can write this as gamma times t minus vx. And we can write this one as gamma times x minus vt. And when we do that, you can see a striking symmetry in the Lorentz transformations for the x and t coordinates, right? And that is in part why we have this symmetrical matrix right here. But let's go ahead and see if our talk matches our walk. So gamma t minus beta gamma x. Factoring out the gamma, I've got t minus beta x. So now beta x is vx over c, but c is 1 in natural units. So we've got gamma t minus vx, gamma t minus vx, as promised. Likewise, let's check the second element here. Factoring out the gamma, we've got minus beta t plus x. So that might seem strange, but that's actually just gamma x minus v over ct, where c is 1 because of natural units, and indeed we have gamma x minus vt here. And finally, y and z remain unchanged. So you can see that this matrix does indeed reproduce the Lorentz transformations. So we have succeeded on that front. Now, we can rewrite this entire Lorentz transformation equation using Einstein's summation convention. So let's do that. How can I write this 4 vector here? This right here is a 4 vector because it's a vector with 4 components. Well, I can write it simply as x to the mu, and I've got this kind of a, actually let me use x to the nu, and this kind of a hat represents that I'm in a new coordinate system, okay, no pun intended. And here, let's call my original space-time coordinates x to the mu. And this transformation matrix right here, I'm going to call it lambda, and lambda is going to consist of mu as a sub-index over here so that it can cancel this one out, and nu as a contravariant index. So don't worry if those words don't make sense yet, I'll cover them. But over here, I'm going to write this entire thing very simply as x bar nu is equal to lambda mu nu times x nu. And voila, we have just summarized the entire Lorentz transformation action in just one simple equation. Now we can do the exact same thing with, for example, this right here is the space-time 4 vector, right? That's the space-time 4 vector where x is equal to t and then x, y, z. Another way we can write that is t and then x with a vector symbol on top of it. But there's other 4 vectors as well. For example, there's the energy momentum 4 vector where p is equal to e, which is just a scalar for the energy, comma, the vector components of the momentum. So that's e p sub x, p sub y, p sub z. That's the energy momentum 4 vector. But we have other 4 vectors as well. We've got a 4 vector for current density. So for example, that would be the electric charge density, comma, the actual current density. So for example, that would be rho j sub x, j sub y, j sub z. And then finally, there are 2 more important 4 vectors that we should take note of. First off is the vector potential 4 vector, A, is equal to the electric potential, comma, the magnetic vector potential components. So for example, that would be the electric potential V, followed by the components of the magnetic vector potential. Okay, this pops up all the time in electromagnetism. And finally, we've got, let's see, the second derivative, or rather just the derivative, okay, partial sub mu. That in itself is a 4 vector for the derivative. So we can write this as partial x, not partial x, we're not taking the derivative of anything, but partial x to the mu, okay? And this is equal to the 4 vector, partial x to the 0, partial x to the 1, partial x to the 2, and hopefully you can see where this is going. So of course we know what x0, x2, x3 are. They're just time and the spatial coordinates. So I can rewrite this as partial t, partial x, partial y, partial z. So that is the 4 vector for the regular derivative in special relativity. So now let's go ahead and dive into the nitty-gritty of contravariant and covariant vectors. So now let's talk about contravariant and covariant vector components. So this is something that tends to confuse a lot of students. So let's try to understand it intuitively. So contravariant vectors come from a very simple idea. Let's say you have a small step, a small displacement in some coordinate frame. So that small displacement, let's call it dx, and it has the components dx to the m in the x coordinate frame. The question is, what are the components of this small step in the y coordinate frame? In other words, what is dy to the n, let's say? Or let's use a different letter, let's say q. Well, dy to the q is very simple to write down. You just use the chain rule. You say it's partial y to the q divided by partial x to the, let's say, some dummy variable, times x to the j, right? That's all there is to it. And that's all there is to a contravariant derivative, contravariant vector components. So you can see it's just a basic version of the chain rule. And what about covariant vector components? Well, those come from the idea of a scalar field. A scalar field is any kind of a field that is made out of scalars. So for example, a temperature field is a scalar field. So everywhere in this room there's a certain temperature, and so that is a scalar field. And so the question is, if we take a small step in this scalar field, in this temperature field, then what's the change in the temperature? Well, it's going to be some kind of a change d phi dy, okay, in the y coordinate frame for this vector. So what is this going to equal? Well, this is going to be partial phi partial x to the dummy variable, partial x p partial y m. So really all we did here is we said, okay, we had a scalar field, for example, a temperature field, and then we took a small step in that scalar field. That small step might have been characterized as dx to the m in the x coordinate frame, but now we want to know, if we measure that small step from the y coordinate frame, what would the change in our scalar field be? What would the change in the temperature be? And the answer comes from a basic application of the chain rule, right? So that is what contravariant and covariant vectors are. So now let's put this to use. First of all, let me write this a little bit more formally. So here I'm going to write this as v to the m is equal to partial y to the m. Let's write m over here. And partial x to the p times vp. Okay, so actually that should be contravariant. Okay, good. So that is one way we can write contravariant vector components. Now let's do the same thing here. I'm going to call this one w sub m is equal to, let's write this one, partial x to the, now this is a dummy here, p partial y to the m, okay, times this right here, let's call that w to the p. So this is how contravariant vector components transform. This is how covariant vector components transform. So now what we're going to do is use this to investigate the metric. So if we want to take the dot product using 4 vectors, here's how we do it. We say that if we're considering the dot product of 2 4 vectors a and b, then their dot product is given by the metric g mu nu times a mu b nu. Okay, so what does that mean? What is the metric? Well, the metric right here is simply the space-time metric given by 1 for time, minus 1 for the spatial coordinates, and 0 everywhere else. Now, this is one type of the space-time metric that you'll see. Another type in textbooks switches up the sign so that the time component is negative and the spatial ones are all positive. That's just as valid. That's very much equivalent. But here we're just using the temporal component as positive, spatial as negative. It's really arbitrary, but as long as you're consistent, it doesn't matter. So how does that explain this? Well, let's go ahead and take a look. This over here is going to simplify to the following. First of all, g mu nu only exists along these diagonal elements, right? Any off diagonal elements are 0. So this is going to simplify to what? This is going to simplify to the temporal components, A0, B0, minus all the other components, A1, B1, A2, B2, A3, B3. Or another way you can write this is that this is A0, B0 minus A dotted with B. Okay, the vector components of the four vectors are dotted together for the second term right there. So that's all you need to do if you want to compute the dot product of two four vectors. Now let's talk a little bit about raising and lowering contravariant indices and covariant indices. So remember that if you have, for example, a to the mu, this right here is a contravariant vector component, right? Because you have mu as a superscript. Whereas if you have a sub mu as a subscript, this is a covariant vector component. Now, how do you go back and forth between these two? Well, you have to use the metric. So for example, if I want to take a to the mu and I somehow want to convert it into a covariant form, for example, a to the nu, then what I'd have to do is multiply this by the metric g mu nu. So multiplying g mu nu by this contravariant vector returns this covariant vector component. So now we can use this to better understand the dot product in four vector notation. So coming over here, let's take a look at this. So we have g mu nu times a to the mu. Well, what is that if not a sub nu? So remember, a dot b is equal to the metric times a to the mu, b to the nu. But now we just learned that a to the mu times the metric gives us a sub nu, right? It contracts the indices. So this right here is a sub nu. So a sub nu times b to the nu, well, that's just a scalar, right? We're just summing over nu because of Einstein's summation convention. And just as well, you could apply the metric to the B4 vector. So let's do that as well. So let's see where I've got space. Let's come over here. So A dotted with B is G mu nu, G mu nu, A mu, B nu. Applying the metric to B, well, then I have B's new component, new index contracted. So now I have a to the mu, b sub mu, right? And so a dotted with b is also equivalent to a to the mu, b sub mu, which is again just a scalar. Now let's take a look at some examples of dot products using four vectors. The first example we'll take a look at is using the energy momentum four vector. So here, consider the energy momentum four vector p. Let's dot it with p. Well, another way we can write that is p to the mu times p sub mu, as we've just found out. But recall that p, the energy momentum four vector, is E, comma p, right? It's the energy scalar, comma the momentum vector components, right? So that's what we have. So what is this going to equal? Well, simply remember that this is g mu nu times p to the mu, p to the nu. Now, this right here is the space-time metric. It comes with a minus sign for all the spatial components, aka in this case, all of these components will come with a minus sign, but it comes with a positive sign for the temporal component, or in this case, the energy component, the first component. And so this is going to give us what? This is going to give us, let's see, we have all of these components are positive. So we have E squared minus P squared. And what is this equal to if not M squared, right? So that gives us the result for P dot P, the momentum energy four vector. Now let's take a look at another four vector. Let's say you have, for example, the d'Alembert. So this is partial mu squared, which can also be written as partial x to the mu squared, x to the mu squared. And this we can write as the four vector partial squared partial t squared times or comma the Laplacian. Okay, or if you'd like to expand that out, that would simply be partial t squared partial x squared, and same for the other spatial coordinates. Okay, so that's all there is to the D'Alembert, partial u squared. And now let's take a look at yet another example. If we have, for instance, partial mu x to the nu, what would that mean? Well, that would mean we're taking the derivative of x to the nu with respect to x to the mu. But of course, since if we're using an orthogonal coordinate system, then this is simply 0. Or if you want to be more formal, this is the Kronecker delta, mu nu, which is 1 if mu is equal to nu and 0 otherwise. So in other words, if you're using, for example, an orthogonal coordinate system, then dx over dx is obviously 1. In that case, mu is equal to nu, but dy dx is equal to 0. In that case, mu is not equal to nu. Now, let me quickly point out the space-time metric, g mu nu. This right here. If you multiply it with another metric with, for example, different indices, nu rho, then this will result in a new Kronecker delta. The nu and nu will cancel each other out. They're being summed over. So you'll have a Kronecker delta with components rho and mu. Why does this make sense? Well, this is actually a definition. It tells us that this spacetime metric with the contravariant components is inverse to this spacetime metric with covariant components. Now, that being said, g mu nu is equal to g mu nu with covariant components for the spacetime metric are equivalent to the contravariant components for the spacetime metric. Just another handy definition. And so finally, the last thing we're going to take a look at is just a simple exercise. Let's say you have lambda. Remember, what is lambda? If not, I might have not defined this before, but lambda of mu nu, for example, is just another way to write dx nu dx mu, just a shorthand notation. But now let's take a look at a brief exercise problem using this lambda. So let's say you have lambda mu nu. So here is lambda mu nu. How can we express it in terms of the space-time metrics? So let me put a space-time metric here. Mu is covariant. And let's put a space-time metric here. Nu is contravariant. And I'm going to put another lambda here. And this is kind of going to look like a diagonalization of matrices kind of example. So I have lambda mu nu. I have mu here as a covariant, nu here as a contravariant. Now I've got to put some dummy indices. Let's put k, rho. So if this k is a covariant here, it needs to be summed over. So it's going to be a contravariant here. And this rho is a contravariant here. So it's going to be a covariant over there. So k and rho are just dummy indices here that were being summed over. And mu and nu are the indices that are going to be left over after they're summed over. So how does this make any sense? Well, just remind yourself of what we learned about contraction. If, for example, I have a contravariant vector component, a to the mu, and I multiply that with g mu nu, then this contracts the vector to a nu. And so now consider applying that contraction rule over here. Here we're contracting kappa, or k, whatever it is, so you're just going to be left over with lambda, and you're just going to have mu rho. And then multiply that by g nu rho. Well, now we're contracting rho, so rho gets summed over, and you're simply left with the lambda. Nu is now contravariant. Mu, as always, was covariant. And indeed, that's what we have on the left-hand side. So that is a simple proof of why lambda mu nu can be kind of diagonalized in this format. So now let's say we have some kind of a tensor. So let's say we have a tensor T with components I, j, k, let's say I to k over here, and with components L to m down here. So it has a mixed amount of contravariant and covariant components. So this is a mixed tensor right here. So the question is, how does this tensor transform in, for example, contravariant or covariant derivatives components? Well, here, if you have the new transform tensor with components I prime all the way to k prime and L prime all the way to M prime, what would this equal? Well, it would equal the original tensor, right? T, I, all the way to k, L all the way to M, but multiplied by certain derivatives. So first of all of these components are contravariant. So let's remind ourselves how contravariant tensors transform. Just write down how that displacement occurred. dym is partial ym dxp, right? So you can see we have partial y, partial x, whereas for a covariant component, for example, the change in a scalar field, let's say d phi dym, that was d phi dxp, dxp, dym. So you can see the change is that for the contravariant components, we have dy dx. For the covariant components, we have dx dy. So you can see that the two fractions are flipped. The two infinitesimals are flipped. And so we can exploit that over here. We're going to write, let's see, partial x to the I. Now this is contravariant, so we're going to have x to the I, and let me denote the new coordinate with this bar and I prime, partial xi, all the way, multiplied all the way to partial x. Our last contravariant component is k, so partial x bar k prime, partial xk. So these are all the contravariant components right there. What about the covariant components? Well, they're going to be in the opposite format. So these covariant components are going to be flipped as follows. So I'm going to have partial x to the L over partial x to the L prime, x bar, all the way to partial x to the M divided by partial x to the M prime bar. And so that is how our tensor T transforms using contravariant and covariant components. Now, I just like to briefly give a word on the Levi-Civita symbol. So the Levi-Civita symbol is just a handy tool in physics, okay? It's written as follows, EIJKL, okay? It's just a scalar, just some kind of a number. Let me write it again here so that it's not obstructed by the light. And so IJKL are just a set of numbers, 0, 1, 2, 3. Now, if you permute these numbers, you can get different values for the Levi-Civita symbol. If you have an even permutation of these numbers, then the Levi-Civita symbol is equal to 1. And an odd permutation of these symbols is defined to give you -1. And if you have neither, that gives you 0. So let's take a look at an example. Let's say, for instance, I switch 2 and 0, okay? So I'm considering e to the 2103. Well, that's an odd permutation. That must be equal to -1. Down here, 2301. And since it's an even permutation, it's going to equal 1. What if you have neither? What if, for example, you're considering e to the 0012? Well, that's just 0. There's no way you can have two zeros in your indices if you permute 0, 1, 2, and 3. There's just not two zeros to be had. So for the final part of this video, the last thing we'll be needing is the Fourier transform. So I'm not going to dive into the math. I'm not a mathematician, as anyone out there who knows me knows. What I'm going to do is just give a very basic, the very basic skim through of all we'll need for the physics. So the Fourier transformation allows us to go between the space representation, the spatial representation of a wave or a function, to the momentum representation, the wave vector representation of a function. In other words, it connects the spatial representation, f of x, with the momentum or the wave vector representation, f of k. So how does it do that? Well, the Fourier transform of f of x is given by the integral of f of x. Now, of course, we're integrating out the x so that we're just left with k. So you already know this is going to be dx, and then some kind of a function involving k. Well, that function turns out to be a plane wave. And we know what a plane wave is, don't we? It's just e to the I k dot x. So you can see all the x's are being integrated out, leaving us with a function of just k. So that's all there is to the Fourier transform. It's just a plane wave times a function. Pretty simple. And what about the inverse Fourier transform? Well, that is simply f of k, okay? And then you have the reverse plane wave, e to the minus k dot x. And here I'm going to be doing dk, so that I'm left over with an x for my input. And then here I'm just going to put a 2 pi as just some kind of a factor that drives people insane. Now, if you have a space-time Fourier transform, then that's just going to be done in 4 dimensions. So that's going to be of the form f tilde of k, 2 pi to the 4th, e to the minus I k dot x, and instead, right, dk. All right, so that's all you have for a 4D Fourier transform. And what if you wanted to do a 4D Fourier transform in this way? Well, that's also pretty similar. In fact, everything is the exact same. Instead of writing dx, I would write d to the 4x, where d to the 4x is simply dx to the 0, dx to the 1, dx to the 2, dx to the 3. Right? That's all there is to it. So another way we could actually write this is, remember what k dot x is, right? So k is some kind of a 4 vector. It's actually a 4 vector given by, let's see, we have omega comma k, I believe. And x right here is a 4 vector given by t comma x. So now when we take their dot products using, remember, dot product of two 4 vectors is not the regular dot product of 2 vectors. It's g mu nu, x to the mu, k to the nu. And g mu nu has negative components for the spatial parts, at least in the metric we're using. And so this is going to give us omega t. So x dot k is omega t minus x dotted with k. So that actually looks very familiar, right? This is just another way to write a plane wave exponential. So this right here, this integral is going to simplify to f tilde of k is the integral of f of x e to the I omega t minus k dot x dx, or d to the 4th x. And that's all there is to the Fourier transform. So thanks for watching this episode of Advanced Quantum Mechanics. We'll see you in the next one.